Okay, everybody. Here today, we're going to go ahead and we're going to work with solving and writing two different types of functions from data. The first type we're going to work with is exponential functions, which we've been working with a lot lately. Anything y equals a times a base raised to the x as an exponent. So it's exponential because x lives as an exponent. That a lot of times in the past it's been 1. So we had like y equals 2 to the x, and we've worked with that. Today we'll probably have a value for a more often. And then we have what's called the power function. And a power function is just that x has a power or an exponent applied to it. So this could be x cubed, it could be x to the third, fourth, fifth, any kind of power. It could also be a 1/2 or a -1. There's quite a few things that could be used as power functions. But our goal is to use one of these two equations to get the equation from data. On number 8, it asks us to find the exponential function that best fits this two numeric sets of data. So what I need to do is I need to plug this in as my x and this is my y. And I'm going to write that down twice. I'm going to do the substitution twice. Once with the 140 and once with the 3 and 640. So I'm going to say 40 equals a, b to the first. Okay. And I'm going to say 640 equals a, b to the third. Now what this allows me to do is to isolate a in one of these equations. So over here, I'm going to get a alone. This is just b to the first, or b. I'm going to divide by b. And that gives me the ability to say that a equals 40 over b. And that b, remember, has a first power. If I take this information and plug it into the other equation, I would have 640 equals 40 over b to the first times b to the third. And if I look here, see this 1 and that 3? If I cancel this 1, this would become a 2. So then I have 640 equals 40b squared. And then if I divide by 40, okay, 640 divided by 4 is 16 equals b squared. So then b would equal 4. And so there's our first step, our first piece. We figured out what b is. Now the only thing we have left to do is figure out, well, what's a? Well, we can actually go back in here and we can do that evaluation now. We know that y could be 40. That would equal a times 4 to the first. Well, that should tell me, if I divide by the 4, a equals 10. So then my equation is y equals 10 times 4 to the x. And there's my answer. I'm essentially finding the a and the b by using two different equations and using a substitution to combine them. Now, we also have problems where we look at it and there's a lot of data and it's not really clear the jump that I'm making from one thing to another. And so what I'm going to do, I'm going to go ahead and try to create an equation. But I first need to build a new table because I want this to be an exponential graph, but I need to know first, is it a good exponential graph? And I need to know what's the rate of change of my exponential graph. So what I'm going to do is I'm going to build an XY table. And this is the way we would do it traditionally and by hand. I'm going to go ahead and create an XY table that uses all of my x values just the way they are, but instead of using y, I'm going to use the ln of y. This is one of the reasons that we like the natural log so much. It really helps us to be able to solve a lot of these problems. So I'm going to run 1, 2, 3, 4, and 5. And that's these 1, 2, 3, 4, and 5. And you know, I think I'm actually going to scrap that and put in a better axis. I want this to be as good as I can get it. Oops. So there's my axes that I'm going to be working with. I need my calculator to help me make these calculations. So I just want to take the ln of each of these values. So ln of 3.3 is 1.19. Okay, 1.19. And then I go and do the same thing. Instead of 3.3, I'll use 10.1. Oops. And I get 2.31. I'm going to go ahead and do it again. The ln of 30.6 is 3.42. And then the ln of 92.7 is 4.53. And last but not least for this problem, the ln of 280.9. Initially, this may not seem like it makes a lot of sense. 5.64. This may not initially seem like it makes a ton of sense, but what we're actually able to do is we're able to create, plot these points and actually come up with a pretty accurate line. So I'm going to go over to 1 and up to 1.19. It's about right there. I'm going to go to 2 and up to 2.3, which is probably about there. And then I'm going to go to 3 and 3.4, which is just under a half. Go over to 4 and 4.5, so we're just over a half now. And then to 5 and 5.64. Okay. And notice that these points, if I plotted the original points, not only would this take off, but I mean, you think about it, I'd already be up to 280 by now, by the time I hit 5. Start out at 3.3, right around there, and then up to 10. This thing would be very steep. It's climbing extremely steeply, and it became difficult to work with. But now, I can actually go in here, and I can connect the dots. What's great about connecting these dots is that now I can backtrack and I can try to find out a pretty accurate idea of what the slope is and what the y-intercept would be. That's going to allow me to find some good useful information for this equation. See, the first thing I need to know is what's the slope of this line. And remember that I'm not talking or writing the equation for this line. This is the ln of y. It's not y anymore. And this is x. And so if we start looking at some stuff, the first thing I want to find is I want to find the slope of the line. It's y2 minus y1 over x2 minus x1. And my y2, I can really pick any of these points over here, okay? And so I'm just going to take 2.31 minus 1.19 over 2 minus 1. So my slope is 2.31 minus 1.19, and that's 1.12. That's an approximate slope there, okay? And then I need to know what's the y-intercept. Where does this cross the y-axis? And so I really just need to know where does it cross the y-axis. It looks very much so to me like this is going to cross at 0. We're very, very close to 0. Typically what we would do is we'd pick an x and y like this, and we'd plug them into the format y equals mx plus b. And we're looking for the b value. So 2.31 equals 1.12 times 2 plus b. And this is going to be 2.31 equals 2.24 plus b. If I subtract the 2.24, I'm going to get 0.07 equals b. This isn't very much. It's a very tiny number. To finish this process, I would write that the ln of y, because that's really my y value, my y-axis here, equals the slope 1.12 times x plus 0.07. Now what I do at this point is I think about the fact that this is ln base e, and I'm going to rewrite this equation so the log goes away. So it becomes e to the 1.12x plus 0.07 equals y. And then I'm going to separate this into two pieces, okay? See, I'm going to have e of point to the 0.07 times e to the 1.12x, which is e to the 0.07 times e to the 1.12 raised to the x equals y. So hopefully this equation works out for me. The things I'd like to still figure out is get rid of this decimal if I can. And so what I'm going to do is I'm going to take e raised to the 0.07 to get 1.07 times next I need to evaluate e to the 1.12. Second, e to the 1.12 is 3.06 to the x, y equals, and there's my equation. And you might feel like that's a ton of work, and it is. There's a lot involved there. I mean, we had to create that scatter plot, we had to do a lot of work with it. We're actually going to find another way to do it using the calculator to help us create these equations. We did this with all of them. We would run regressions. Well, it is possible to run an exponential regression. And I'll show you how to do it with a power regression, and then you can just change the regression you run to exponential. 15, we're going to speed the process back up. We're going to go back to a basic equation. We have the power function, which is y equals ax to the b. And again, we need to know what a and b are. So I'm going to plug this in twice. I'm going to get 3 equals a times 4 to the b. And I'm also going to get that 15 equals a times 15. Whoops, I got that back. Equals to the 8 to the b. There we go. And I'm going to use this first equation to get a by itself. So a equals 3 over 4 to the b power. I'm going to take this and plug it in right there. So we get 15 equals 3 over 4 to the b times 8 to the b. Just so that I can do some canceling, that's kind of my goal here. I need to be able to do some canceling. I'm going to rewrite this as 15 equals 3 over 4 to the b times 2 to the b times 4 to the b. If you think about it, 2 to the b times 4 to the b is 8 to the b. Okay, so that's our thought process here, is that we can separate them. The reason I do that is so that this and this will cancel. So we're always trying to match the denominator if possible. And then I'm going to get 15 equals 3 times 2 to the b. Whoops, I let it slide down a little too far. 3 times 2 to the b power. To get the b alone, I'm going to first divide by 3. Get 5 equals 2 to the b power. And then whenever I need to get an exponent out of the exponent position, I have to create a logarithm. So this is the log base 2 of something equals my exponent b. And this is going to be a 5 here. So I need to take log base 2 of 5 and put that in the calculator. Oops. So I'm going to come in here. And remember, when you're doing log like this, you need to change base. So it's log of the 5 divided by log of the 2. And we get 2.32 equals b. And then I need to plug that in here to find a. So a equals 3 over 4 to the 2.32. And I'll go to the calculator. Keep grabbing the wrong one. Go to the calculator for that. It's 3 divided by parentheses 4 raised to the, I'm just going to grab the answer. You could type in 2.32. I'm trying not to round. And I get 0.12. So a equals 0.12. That means my equation is y equals 0.12 x to the 2.32. And that's how we build the power function. It's very similar to the other one, just that the x is not an exponent in this problem. And so that was number 15. We need to look at one last one, and here's where we're going to use the calculator to run this regression for us. Instead of that whole process, this one would require you to do ln of x compared to ln of y, which means we'd have to put each one of these into the calculator and evaluate the ln, the natural log, graph those results, create the equation, and go through quite a process to do that. For now, what we're going to do is we're just going to go ahead and go in and do a statistics analysis. We are going to edit our lists so that it has 1, 2, 3, 4, and 5. Those are my x values. Then I need to put these y values in as 2.5, 3.6, oops, 4.7, 5.5, and 6.2. Now you may or may not have noticed, but at first it's going up by 1.1, goes up by 1.1 again, and then it only goes up by 0.8, and then it only goes up by 0.7. This reminds me a lot of a decay function or something that's flattening out. It's going to stop climbing very much. So maybe a square root on its side, something like that. So we're looking at that idea. Now that we have that in there, we're going to go to stat again. This time we're going to calculate. And we did, before we've done quadratic regression, we've done cubic regression, even a quartic regression once in a while. Then there are two down here. There's the exponential regression, which we could have used on problem number 12. It would have worked on problem number 12. We're going to use a power regression. We have a power function here. So depending on which one you'd want, you're going to use one of these two. And so what I'll do is I'll go ahead and run a power regression. Now I have to, with this kind of calculator, this older calculator, tell it which lists to use as x and y. The newer calculators don't require that. So I'm going to go ahead and hit enter. And it gives me 2.48, we'll say, and 0.57. So I'm thinking about the power regression, and it gives me the equation here. So y equals 2.48. X to the, and we need to know what the equation was. The equation, or the b was 0.57. So 0.57. And there's the equation of our power model, our power function, for question number 25. And you know, there's going to be the small variations. The book I think has 2.5 here, and it has 5.67. Those are very, very close, very accurate numbers. Again, the alternative to the calculator regression is to build the ln of x, the ln of y. All these is ln's. Now plot the points, find the slope of the line. It's a process. A process that I think is more involved than what we want to be working with at this point in our math career. So hopefully that helps. Hopefully you have enough work. Remember back when we did number 12, this could have been done using these points, original points, and doing an exponential regression. My goal is to have you do that in class so that you have that taken care of and there's not as much of a problem. Good luck, and we'll see you in class.